Hello, welcome to this academic project demonstration. My name is Charles Matthew with student number 10529938. This is an academic project demonstration to Edith Cowan University under ENS 6146 Instrumentation and Measurement Unit. The aim of this project is to design, erect and commission an instrumentation temperature measuring kit using a resistance temperature detector. The entire demonstration is subdivided into different categories, namely an introduction to the hardware implemented, interfacing the hardware circuit with software and programming, and finally testing of the sensor to determine its static as well as dynamic performance and the control action. Without wasting time, let's get into the demonstration. This is the circuit which I have designed, which comprises of several components. So this is the primary sensing element, which is PT100 RTD type A with a 3-wire configuration, and it is connected to the circuit board using IEC 60751 standard. So one of the major problem with an RTD is that it generates an output in resistance or ohms, so which cannot be directly interfaced into a circuit board or ADC board. So typically in industrial applications where we interface an RTD sensor with PLC or DCS using RTD modules. So in our case, I have designed an amplification circuit. So the amplification circuit, the output of RTD in resistance is given to a voltage divider circuit, which is formed using a 1 kilo ohm resistor, a 5 volt constant voltage source which is taken from the ADC board itself, and a variable resistor which is nothing but the PT100 RTD. So when the resistance changes according to Ohm's law, a voltage will be generated. But the voltage generator is 0.4545 at 0 degrees Celsius. So typically the LRV or lower range value is supposed to be 0 at 0 degrees Celsius. So as a result, I'll be using a differential amplifier. So the differential amplifier is again custom made. I have used an LM234 operational amplifier, this one over here, the black one over there, to perform the amplification. So this LM234 operational amplifier, together with a constant voltage source, which is the actual output, which is 0.45 volt, it is made constant using a variable resistor of 10K, and it is adjusted to output F constant voltage of 0.4545 and another resistor of 47 kilo ohm. So what the differential amplifier does is that it will subtract this 0.4545 additional voltage from the output and makes 0 volt at 0 degrees Celsius. Now that this zero calibration is done for the sensor, and the output generated by the RTD in volts will now be calibrated output. But the output generated is prone to different noises, and the SNR is very low with this existing circuit. As a result, I'll be using a 100 microfarad capacitor to perform low pass filtering, and the output is again stepped up using an LM234 operational amplifier based voltage follower circuit. I have used the same terminals of the LM234 op-amp for this. So it will be stepped up to produce a gain of 0.2264, but it is still not matching with the 5 volt rating of the ADC board. As a result, I'll be using an internal ADC supply of 1.1 volt to step this up and produce a gain of 4.85 volt, which is almost identical to the 5 volt rating of the ADC board. So this output, which is a conversion of resistance measured by the RTD into voltage, is fed into the A-node pin, which is the analog input pin of the ADC. Analog input pin, I'm just trying to zoom it. Yeah, analog pin of the ADC. So the ADC board converts this analog output into your digital outputs, and it is displayed for monitoring purpose. So now let's get into, and you have a serial 16:2 alphanumeric display to show the values over there, and Now this is interfaced with the PC using serial communication, which is called the Serial Communication Protocol UART, or Universal Asynchronous Receiver Transmitter Protocol, and it is interfaced with the PC using a Type B USB cable. So this is a program which is used for programming and monitoring, or act as the basic HMI. So once this is turned on, you will have the program. So this is the basic program which I have coded for this skit, which has different parameters, like different variables which are used for display purpose, like the temperature, slope, R naught, alpha value, and C value, or everything which is calculated, and you can refer to the report for further details. So then the most important part of this is this act as the interlock for this program, so which turns on an LED which is connected to the pin 13. Let me zoom it. Yeah, pin 13, which act as the digital output pin, which will get energized when the temperature reaches more than 50, and as a result there is an LED which is connected and marked as yellow over here, which is directly integrated with the pin number 13. This will be energized. So this is actually a demonstration of how this board is used for controlling a process, or you can simply say it is the control action. So now let me I'll be verifying this program. So once it is verified, now I'll be uploading this to the microcontroller itself, and let's see how it will perform. So it's getting uploaded now, and now let's see how it, now the microcontroller is turned on, and you have the display over here. Currently it's sensing 29.71 degrees Celsius and a conversion of 85.21 degree Fahrenheit, and the corresponding voltage and resistance value is also matching over here. If you compare this resistance and temperature with an resistance temperature chart, you can see that they are matching. So now let's compare the static performance. So now the RTD is sensing the ambient temperature, which is 29.56 degrees Celsius. Now let me Google to see what is the ambient temperature over here. Yeah, it is showing around, let me update it. Yeah, it is showing around 29 degrees Celsius, and our circuit is also matching with that, so which means the static performance is pretty much very good. So now another way of displaying this is using serial monitor. This is actually basically, you can call it as an HMI. So this will also provide you the instantaneous values, and the values again matching with what is being shown in the display, which is 29 degrees Celsius. So for the purpose of demonstrating the dynamic performance, I'll be using something called a serial plotter, which will give you a plot indicating the instantaneous value, so we can easily identify how the sensor responds to sudden changes in the temperature, and how a gradual reduction of temperature results in a gradual curve. So for this purpose, let me heat this, and meanwhile while heating, when the temperature reaches 50 degrees Celsius, I want you to notice the pin number 13, which is the digital output, energizes, and the corresponding LED which is marked as L will get energized, which is the control action, demonstration of control action. So let me heat it up. Okay, now the temperature is rising. It has crossed more than 50, and you can see the LED has energized. So the control part is successful. So now let's see how the static performance is. Yeah, you can see the shoot of temperature over here. It has increased from 29 degrees to more than near to 90 degrees. So once it reaches there, I have removed the temperature, I mean the heat source. So then the temperature started declining, and you can see the smooth curve which is following, which means the linear relationship of this sensor with the temperature. So the temperature is pretty much linear. So that proves that the sensor is having high static as well as dynamic performance. So So that's it, and that's the demonstration of the measurements kit. And in an industrial setup, this can be scaled up. The temperature, this will be, RTD will be the same, or you can have different types of RTDs, including PT100 and PT1000. And this circuitry will be replaced with professional transducer circuits, or you can say that RTD modules, and the RTD modules will be connected to PLCs or DCS, which will be replaced in our case with the ADC board, and the HMI will be replaced with the DCS SCADA systems. So these outputs, like the DO, can be digital output generated, can be used for controlling valves, fans, drives, etc., for controlling the process and stopping the process from safeguarding the system from imminent dangers. And also the analog output can be used for monitoring purpose, as well as those analog values can be used for continuous monitoring and as an input to PID controllers for fine-tuning the processes and improve the efficiency. So I hope you have enjoyed this presentation, and I hope it was an informative session. So I recommend the viewers to refer to the project report for further details. Thank you.